Alright, go over our final review packet. First one, problem number one, what's the area between the graphs? Well, graph them, zoom in on where they cross, and you put the g function is on top, the f function is on bottom, and -5 to 3. You can use your calculator for that. A lot of computation, you'd probably be given a calculator, but hopefully you can do it without it too. On this one, the average value, what's the same thing? We're doing the integral from -6 to 1 of sine of x. Make sure you're in radians. However, we're dividing it by 5 out here because that's average value. Remember, average value is when you divide it by 5. You should know that this gets separated immediately to this. If you separate the variables, this is when you want to memorize. The 2 goes up with the x, and the e, and then the c value. And then if you plug in t is 0, or x is 0 in this case, it should be x here, you'll end up with an 8 for a constant. So you want to memorize this. When you have dy dx and y over here, it's this exponential graph. This is simply chain rule down, or sorry, not chain rule, quotient rule. Low d high minus high d low over low squared. Pick out the values you need, do the computation. The side of a cube. The volume of a cube is side times side times side, right? If you have a cube here, it's side, 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 volume is this. Then you can differentiate with respect to time, dv dt, 3s squared, and don't forget ds dt. And then you're given a side and you're given ds dt, put them in there, and now you have the change in volume. This is the second fundamental theorem of calculus that says if you want a derivative of this, you just take the derivative, and if you want a derivative of an integral, cancels it out, and this x drops down here. And don't forget to do the chain rule, but in this case we're doing the chain rule of this expression up here, so the chain rule is just times 1. Had that been 2x, we would have put a 2 there, but chain rule of this in this place. And then you can plug in 2. Points of inflection are when the second derivative is 0. There are other options when the second derivative is 0, but the majority of the time it's just the point of inflection here. So these two, and don't forget we're taking the derivative, so we multiply and subtract. Don't make this -10 there. Alright, on the second page, instantaneous rate of change is another word for slope, which is another word for derivative. Take the derivative, plug in 100, and there you have it. Low d high minus high d low. You can leave it like this on the AP exam. You don't have to simplify that denominator. This is a disk method because it's touching right there. Pi r squared, 1 to 3. We have a function. Take the derivative, plug in -2. On number 3, remember this is an exponential graph, just like e to the x, and the derivative of e to the x is e to the x, but there's more to it than that. Remember, it is ln of e and 1. It is ln of the base and the chain rule right here. So 3 2x squared stays the same. Natural log of the base 4x. We have the derivative here. It is just pull down the 1/2, subtract 1. Don't forget chain rule. Derivative of cosine of 2x is negative sine. But again, don't forget the chain rule again. It is a 2. This is a 2-step chain rule problem. Number 15, we want the 14th derivative. That's what that says here. The 14th derivative of sine. Well, if you look at sine, if you take the derivative of sine, you're at cosine. Derivative of cosine is negative sine. Derivative of negative sine would be a cosine with a negative, and the derivative of a negative cosine would be a sine with 2 negatives back to positive. So what you see about sine is every 4 derivatives you're back where you started. 1, 2, 3, 4. 1, 1, 2, 3, 4. So if I do the 14th derivative, 14 divided by 4 is 3 with 2 left over. That tells you you're going to do 3 laps and then 2 derivatives. 1, 2, we're at negative sine. So the 14th derivative of sine is negative sine. Then you plug this into negative sign and you have negative root 3. 16 is a Riemann sum problems. Remember the start of January when we were doing all the Riemann sums here? And what you have to be able to see in here is that this integral right here matches this Riemann sum. I'm doing an infinite number of rectangles. That's what this says. From 0 to 5, so that's a width of 5. There's a 5 out here. And I'm going to start at 0, so 0 plus this rectangle. Remember we took this width of 5 and divided it by the rectangles, and I stands for the steps you're going to take. You're going to take an infinite number of steps. So you want to be able to go from here to here, and then they simplified this down to here. I think the key on these is that this is a gap of 5 right here. The gap here is from 0 to 5, which is 0 to 5, and we're going to divide that up an infinite number of times. So this is a key right here. You can usually tell by that number right there which one it's going to be. In this case, they're all 5s, but a lot of them that I see, you can get pretty close if you do this and know it starts at 0. And then what you see is x plus 1, and that's what this is. This is the x plus the 1 right there. All right, 17, hard integral. So what do we do when we have a difficult integral to do? Well, we do u substitution, and that's what I did here. I took the denominator, let that be u, derivative all the way down 1/3, and put the 1/3 over there, and there's a 2 here already. So we have 2/3. When I added 1, I divided by this, which puts a 2 out there. No calculator. This could be divided up evenly. You could do the quotient rule, but if you can simplify it, it's much easier. The derivative of a function is given by this. When is the function increasing? Well, what are the critical points? The critical points are when the derivative is equal to 0. Now be careful here because they already give you the derivative. A lot of times we have to find the derivative. They've given us the derivative, set it equal to 0, plug your point in there, and then you'll see what's going on. But I know a lot of times we take the derivative. Be careful, you're given the derivative. All right, piecewise function. Let's check if it's continuous. Well, I plug in 2 because that's the point in question right here. We don't know what happens at 2. If I plug in 2, they both come to -3, so I'm safe. It's continuous. And this one's pretty self-explanatory. If they're coming together, then it's definitely a limit there. Both of them are going to 2. Is it differentiable? Well, if I take the slope of this one, it's -1. If I take the slope of this one, it's -1/2. It's not differentiable because the slopes don't match. Right here, let's see here. This is, again, I integrate something and differentiate it. These go away, and this drops down into there. So now it is x cubed squared, which is x to the 6. But again, always remember that this chain rule needs to happen. So that comes down there. I usually write that in front, simplify that one. Just a basic integral sign goes back to negative cosine. Have to know your unit circle stuff there. Horizontal asymptotes are what happens when we go out to infinity. So if I'm going to infinity, the only thing that matters is the front end. Be careful, this is the highest power, this is the highest power, and if I simplify them down, I get -2. You could continue to, if you want to use L'Hopital's rule, where you just keep taking derivatives, this would be -36 squared, that would be 18 squared, and what you'll see is this top is always twice as big as the bottom, so that'd be -72x, 36x, get rid of that, -72, 36, and again we're right back where we are right there. So either plug it in and simplify, or just take L'Hopital's rule and multiply it all down. A particle's position is given by this equation. When is it at rest? Well, that means when the derivative is 0, when there's no movement. That's what derivatives are. They are movement. There's no movement in this at 2 and 6. 25 average value. I just got to be careful. Usually they say this goes from like 1 to 3. So this goes at the bottom down here. I know it's easy to put the 3 on top and then we just subtract them back. I just plugged it in my calculator. What I got exactly, well, I got on my calculator was this, but if you do it by hand, you'll get 3 over pi. Same thing. This one's a little tricky here. What to do? We're integrating something that's a little bit more confusing than normal. So I did some u substitution, and if I let u equal ln of x, then the derivative of ln of x is 1 over x. You can multiply the dx over there, and I have dx over x. And that's right here. You can see that's right there. And then I have ln squared, so that's u squared. And since I'm doing a definite integral, I went ahead and changed these. If you run these numbers through here, if you have ln of e squared, well, that 2 can come down, and it's just 1, so that's just 2. Put a 1 there, that's 0. So now you can just use these numbers with u. You don't have to substitute this back in because you have a definite integral. This problem didn't work out well, so we skipped that one. No calculator here. A little bit tricky what to do, but if you make u x squared plus x, the derivative of this is 2x plus 1, which is right there. And now we have e to the u du. And again, I'm going to stay in the world of u by running these numbers through this u function right here. 1 plus 1 is 2, 0 plus 0 is 0. Now I can forget about the x's, do all my work here. 29 shows a derivative graph, and the area under it gets us back to the number of bottles. So what was happening here? There was a leak, he fixed it, the leak stopped. This area is the amount that was lost, and I just integrate it, which means find the area. Geometric shapes here. Rectangle, triangle, triangle. On the rest of it, you have a College Board video. I recommend you watch all of them. We've watched about half of them so far. This is another one, video number 8 from 2023. You can go back and watch the other ones if you want to. Even if you don't take notes on them, it is good just to hear this stuff again. This is an excellent one. This is from last year's test. The College Board releases them every single year. The video is posted in Canvas, so make sure you go back and watch this one. This one's a great one to really learn how to do, because it is very tricky at the beginning, because you have a graph here of some areas, and you can find those. I mean, the first thing that should pop in your mind is geometric shapes. So even if you don't know exactly what to do down here, there's a good bet you can integrate something. And since you don't have a function to integrate, you could just find areas under here and put something together. For example, if we're going for f of 5, maybe it means all of this area here. From 0 to 7, maybe that means all of this area here. You can go ahead and put the areas together, even if you don't know what exactly you're doing. Don't leave it blank. Watch the video on it. It's excellent. And the video series also covers a lot more questions that he has posted, so that's good. And the last page, this was originally supposed to be part of our quiz, but we didn't get it done. So we have this function here, and I factor the top and bottom. Zeros are numbers that are going to make it 0, and the only one that's going to work here is this -1. Whoops, I have it graphed in the wrong spot. -1. So there's this 0 over here where this graph touches. If you plug in -1, you get a 0. Anywhere else you plug in, you can't get 0. Because if you plug in -3, well, that's going to be undefined because I'll have a 0 at the bottom. But it does come out, so it is removable, so there's a hole there. And if you plug in 6, you'll get a 0, but 0 is in the denominator, so that's an asymptote. So there's only one 0 here. The only true 0 is -1. which hits the graph right there. And you should graph this. You should go to Desmos and type this in, and you should get a picture, something like this. My lines are probably going in the wrong spot, but there will be an asymptote here. There will be a 0 here, and there will be a hole there. So check it out, see what it looks like, but those are the 3 points that you need to know. Particles moving along, how much does it travel during the first 5 minutes? Well, this is its velocity. So if I integrate velocity, I'm back to position. Position, velocity, acceleration. And here, this is meters per minute. This is meters, and this is meters per minute squared. And those are the units, and this is where I start, and that's where I want to go. So I just integrate that. On this interval, what's the maximum speed? Well, the things to check by the extreme value theorem are 0 and 5. And I also want to check where it's equal to 0. So where is this equal to 0? So my function is velocity is 16t minus t squared, but I'm not setting this equal to 0 because I'm not looking for a max position. I'm looking for a max velocity. So I'm maxing up this equation. So this is the one I take the derivative of. And this gives me the 4. Plug those in there. 32 is the highest. Don't have to check anything else but the endpoints and points where the derivative is undefined or 0. And again, why does this work? If you had a question and it said, why does this work? Or it said, justify, you could say the extreme value theorem when it's continuous and differentiable. This function is continuous, it is differentiable, so this is the main one because the extreme value theorem says when it's continuous and differentiable, there is a max or a min. And this function is, so you want to say this function is continuous because it's a parabola and parabolas are continuous. All right, we have a washer method here. It is pi big R squared minus pi little r squared. There's the big radius, top, bottom. There's the little radius, top, bottom. If I draw it, here's the little radius. If I draw it, there's the big radius. And again, got to do some integration. What do we do when it looks tough? Well, use substitution. If you let this equal u, do a little bit of computation here, you can get it to match 15x plus 9. And that's what I have. Derivative secant. Secant tangent, pi over 4. Use your unit circle. The notation here is secant tangent at pi over 4, and we get root 2. All right, hope this helps with your review. Again, spent a lot of time in Khan Academy, and good luck on the test. I will see you tomorrow.